Okay, so my research focused on multiple systems, especially exploring the capabilities of the Roman Space Telescope in detecting such systems. So in this study, I have concentrated on triple systems. So in general, we are all familiar with the fact that the demography of discovered planets have grown significantly in recent years. Most planets have been discovered using the transit method, primarily thanks to space missions like TESS and Kepler. But however, we know that microlensing allows us to explore regions inaccessible to other methods. An interesting point is note that among all the multiple systems discovered today, only the 40% are truly multiple systems. This indicates that there is still much we don't understand. Since planets form from protoplanetary disk, multiplanetary systems should be the majority. However, this is not the case, likely due to our technology limitation. So in this plot instead, we can see all these planets that have been discovered inside the multiple systems today. And the obvious limitation of this plot is that for most systems discovered via the transit method, we don't know their mass. However, it's still useful in understanding which regions have been most explored by each method and how microlensing play a crucial role in sampling areas that are less accessible to other techniques. So with the upcoming launch of the Roman Space Telescope, we expect to observe many more light curves that can be attributed to multiple planetary systems. And here we can see that in our literature, we have only few planets that has been discovered in multiple systems. So we expect to observe light curves similar to this one, where the presence of three distinct anomalies inside of the curve suggests the existence of three individual objects. This is a planetary with two giant planets, or another sample is this one, where we have a triple lens model that is not even so evident, but in the system here there are an Earth-like planet and giant planet. So to do these things, to prepare for analyze the Roman Space Telescope, we need to code to calculate the magnification. And during the last year's conference, I had the opportunity to introduce VBMicrolensing, the code developed in collaboration with Valerio Bozza. And many of you are already familiar with the updates on this, so I'll be very brief about it. And today the code has been public, available for from several months on GitHub. Additionally, the paper has been submitted and accepted for publication, and is present on the archive. In the case of multiple system, the primary challenge is with the counter integration method is solving the polynomial associated with the lengths, because we have a lot of numerical noise when we have more than two lengths. So we have solved the problem with two new algorithms that you can find in VBMicrolensing. Two new algorithms, multi-poly and no poly. The single poly is the generalization of the classical polynomial solution, but it has some problems that we have solved with multipoly and no poly. The multipoly calculates the polynomial for each reference frame centered on a length, reducing errors for roots close to that length. And the no poly use an expansion of the length equation, so avoid the use of the polynomial. But what are the advantages, disadvantages of this method? So here are some plots from paper, and the single poly methods in reality can still be used in certain systems, as shown in this plot, which illustrates the condition under which the code fails based on the masses of the second and third planets. in a triple system. So here we can see that the code remains effective when at least one of the two planets is a Jupiter planet. In other case of triple lens, the best performing code is the multi-poly, which proves to be the most robust and also faster than no poly. And this plot is evident. Here we can see computation times for the three algorithms across for triple lens configuration as the magnification varies. We can observe that the multi-poly outperforms no poly in terms of speed in triple systems, but in this final comparison plot, we can see that if the number of lens increase, the no poly is more robust. We have the dot lines mean that in that region the algorithm is not robust. So no poly remains robust even for systems with a greater number of lenses. So the idea was to use this code to explore the potential of the Roman Space Telescope in detecting multiple systems, particularly the triple planetary system. So the triple system, so with a star and two planets. Triple systems, like this one that we have in literature, this systems have this system we have a star that is really similar to our sun and two gas giant planets. The approach was take the lower mass planet that here is labeled as Q2 and reduce its mass to determine the point at which the Roman Space Telescope would still be able to detect the third planet. So we have simulated the experimental data for the Roman Space Telescope using the triple lens model from VBMicrolensing, and on this simulated data we have performed a binary lens fit, and if the fit results in a very high chi-square value, it indicates that the third planet is detectable. And here we have a simple example with the triple lens fit, which obviously match the simulated data well. So starting with the mass of the planet from the literature, we see that the planet is easily detectable as the chi-square per point is quite high. And next we observe what happens when we reduce the planetary mass. And here we can see that with 10⁻⁴ is still visible, 10⁻⁵ to 10⁻⁶ no, and 10⁻⁷ no, because the chi-square is really low. So, so what we did next was run an intensive simulation across various configurations, always considering the case where the source passes close to the central caustics. Okay, because we want to study in what case, in how many cases we can see the third planets when the source trajectory is really near the central caustic. So we built this configuration based on the simulation from Matthew Penny's group, and this simulation the simulation of Matthew Penny's group focused on binary events detectable by the Roman Space Telescope. And what we did was take two of these systems with similar stellar masses and combine them to see if, even when combined, the Roman Space Telescope is capable of detecting the third object. So here there are some preliminary results, and on the left we have a graph plot showing the mass ratio between the third and the second object, and on the right the parameter of the third object, and the color indicates the success percentage for the configuration within the parameter space, that parameter space. And we observe that the success rate is very high, especially when the planets are massive, as expected. But in general, it's important to note that approximately the 70% of the simulated light curve allow the detection of the third planet. So here I have one of these cases, one of these successful cases. In this plot, we show the caustic of the binary systems and the system when the third planet is added on the right, and with the parameters that I have used in this simulation. And we can see here that in green we have the best binary fit, and in blue the true model that is a triple model. And we can see that this is a case where the third planet is visible. So in conclusion, in the final plot, I wanted to add the parameters of planets that could potentially be detectable within the plot that of planets presents in multiple systems that we have looked earlier. And this gives us an idea of the regions that the Roman Space Telescope should focus on sampling more effectively. And so in conclusion, so we have explored the capabilities of VBMicrolensing, and we have used it to understand the capability of Roman Space Telescope, and we have seen that the Roman Space Telescope will be able to detect triple system, not 50%, 70% of the simulated events. So yeah, thank you.
I have one question for all your noise that you injected. Was it all uncorrelated noise, or did you add anything systematic?
Sorry, there is a really high echo, and I haven't.
We'll try again. I was asking about whether the noise that you added was uncorrelated or it had any systematic errors, red noise.
Oh, okay. No, I have. I did just a Poisson noise.